Hello, welcome to my thesis presentation. The topic is model-agnostic personalized federated learning using adaptive client selection. So first, problem formulation. So the idea is that we have client I having a very small amount of data, and we want to use information from other clients to train the model for client I. The problem is we cannot share raw data between clients. So how do we share the knowledge or information? One way is to evaluate the contribution of a candidate by using the change in validation loss. Which candidate help the loss decrease the most will be selected. Here we assume that data could form some kind of clusters, but we don't have any knowledge about the clusters. We just know that data in the same cluster will have the same distribution. So that's basically the main idea of the solution. For methodology, we basically have two algorithms. Actually, it's two versions, one for parametric models and one for non-parametric models. First, let's talk about the one with parametric model. Here, each client will have a model parameter W. We want to improve W by sending W from client I to client I prime. And then the parameter will learn from the whole new dataset and improve itself using gradient update or gradient descent. After learning, client I get the parameter back and compute the reward from this new W, as mentioned, by using validation loss. After all, the one with the largest reward will be selected and update the model for client I. And this is for one iteration. We do this many times until the model converge. So that's basically the first algorithm. Now let's recap a little bit how gradient descent work. Basically, gradient descent tell the model to move to the optimum step by step by computing the gradient. It means that we should have an explicit W. But what about non-parametric models like decision tree? They don't have any specific parameter. In this case, we can approximate the gradient update by finding new models that reduce the loss but still stay close to the current model. The problem is, how can we divide the distance between the current models and the next model? An idea is that we can compare their prediction on a label or dataset. The workflow would be like this. Client I could send the current model and the test set to client I prime, and here we can calculate the update and then send a new model back to client I. That's basically the idea of the second algorithm, which is used for non-parametric models. Please refer to the report for more information. Okay, so let's move to the experiment section. For the first experiment, we use synthetic data. Basically, we divide two clusters by creating two true weight vectors. So each client will follow one cluster and have one true weight vector to generate the data point, the local data point. So here note that each client just have a small amount of data. First of all, we can see that our algorithm perform really well compared to the baseline model. Here, the baseline model means that each client just do the gradient update on its local dataset only, while our models use knowledge from other clients as well. Then we also test the effect of dimension size, and we can see that higher dimension give higher loss, which is understandable because it's more complicated to learn. Then we test with other parameters as well, such as candidate size. We can see that too few candidates would give kind of poor performance, but too many candidates will also give a poor performance. Here, for example, we have 2 candidates. It's very poor right here, but for 8, it's better. When we have more, the loss become higher. We also test the sensitivity of our algorithm with noise, and we can see that as the noise higher, but the loss increase much higher, and difference between each increase is also bigger. Like from here to here, it's small, but like from here to here, it's much bigger. We also compare our algorithm with IFCA, which is a very famous personalized federated learning algorithm, and it seems like our method performs better with a much lower loss. So let's move to the non-parametric experiment. Here we created a synthetic data like this. Create a synthetic data like this, and we divide them into many clients. Here we use decision tree to classify, and when we look at the partition figures, we can see that the model slowly capture the pattern. It shows that using our algorithm, the model can learn the overall distribution pretty well. However, the log loss is not really good because data points close to the diagonal, here the diagonal line boundaries, those data points that close to it is misclassified a lot. Finally, we test the ability to learn a regression problem with non-parametric models. We create a synthetic data like this using a quadratic function. And here we can see that at first the model doesn't approximate the distribution very well, but then after a few iterations, the lines look more similar to the ground truth. We also can see using a more complicated, like random forest here, results in a better approximation. However, after all, these 2 models still converge. This shows that our model is model-agnostic, meaning that it performs well at some levels regardless of the models. Algorithm perform pretty well on regression problem, and for classification using decision tree, it still can capture the overall patterns, meaning it still learn from other candidates as well. This seems like a promising approach because it's performed really well on a practical dataset such as Fashion-MNIST, and it's outperformed really famous algorithm IFCA. And finally, this is a model-agnostic method because it performs pretty well at some levels regardless of which model are selected. And thank you for listening to my presentation.